Hi, everyone. My name is Aidan Lakshman. I'm a PhD candidate at the University of Pittsburgh, and I work with Dr. Eric S. Wright. Today, I want to talk about Exolabel, which is an algorithm we've developed in R for community detection for big biological networks. Just to introduce the problem, networks are one of the most classic data structures in computer science. We have some collection of nodes with edges between them that imply some sort of information. Now, these pop up all over the place. We have things like social media networks where each node is a person and the connections between them are if they're friends. We have things like geographical networks where we can map for like towns or cities with the edges being how often people travel between them, and many, many, many other contexts. One of the classic questions we ask is, what are the communities within a network? So which nodes are more densely connected than others? Which implies different things depending on the context. But for instance, in social media land, it could represent people that are all mutually friends with each other or that often communicate. Now, one of the questions that we need to have an answer to in my field of comparative genomics is what genes are the same across organisms? And I'll get to why that's relevant in just a second. Sort of the modern era of comparative genomics, we have too much data to analyze by hand in a biological way, like in the wet lab. So a common technique is to analyze a small set of organisms or model well-studied organisms, identify pieces of that well-studied organism that are the same as less well-studied organisms, and then transfer the information we have in this context to much broader scenarios. And in order to do that, we need to know what genes are the same between that well-studied group and everybody else. So in short, we need some sort of gene family, right? Where we have these two, for instance, gene families where all these genes are the same across organisms. All these are the same across organisms, but they're not the same between. So 4 and 8 are not the same gene. Now, unfortunately, finding these gene families is not a trivial problem. The pipeline by which we typically discover these is to start with these genes as sort of just genes in a bag. In between each pair of them, we do some sort of sequence similarity comparison. There's a lot of ways to do it. The most common is BLAST, but there are many others. And as we do that between every pair of genes in our set, we get a large network where our nodes represent genes and the edges represent how similar those genes are at the sequence level. Now, if we weight each of these edges by how similar the genes are, we end up with what we call a sequence similarity network, where thicker lines, in this case, are indicating more similarity. You can see we have two pretty well-defined clusters or communities, one on the left and one on the right, but there's still a couple spurious edges here that connect the communities even though they're not correct. This is where community detection algorithms come in. Their job is to take this sort of network structure, cut edges that are spurious, identify what the spurious edges are, cut them, and identify the final community structures. Now, in the context of comparative genomics, these final community structures form our gene families that we can use in sort of downstream analyses. So for this talk, I want to focus specifically on this step of community detection. Given some network, community detection algorithms, again, identify communities. To put it in a more concrete way, the inputs of any community detection algorithm are some graph defined in the usual way with nodes and edges on the nodes. And the output is some node labeling such that two nodes are in the same community if they have the same label. A more intuitive way, I think, to think about it is a sort of a node coloring. So we start with this graph that is all gray with nodes and edges. And the community detection algorithm determines essentially colors for each node such that two nodes are in the same community if they have the same color. So you can see all these nodes, these 6 in the top right are in the same community, but these 2 on the side are not because they're different colors. Now, many algorithms exist for community detection. Between 2004 and 2012, there were 11 algorithms developed that I could find on community detection, probably many more, and many after this as well. The reason that there's so many algorithms for community detection is because this is a widely applicable problem in a lot of different scenarios. So people have come up with different approaches depending on the use case and depending on different ways to optimize for community detection. For instance, all the orange algorithms here are optimizing something called modularity. The blue ones are trying to apply mathematical or physical models to network structures. The purple ones look at sort of random walk-based approaches. And because each of these are developed for different things, or at least are optimizing different things, when we apply them to some sort of network structure, each of them are going to give different results. So here's 4 different clusterings of or communities detected on the same central network here with different algorithms. You can see that there's a lot of similarities amongst them. For instance, all of them determine that this glob here is all the same community. All of them determine that this glob here is all the same community. But there's also a number of differences. For example, this blob in the top right differs based on which algorithm we're looking at. In the bottom right, this is determined to be all one community. In the top left, you can see that it's in 4 different communities. We have one in which it's 3, and in the top right here, it's 2 different communities. Okay, so the question here is which one of these is right? Which should we be using? Is it actually one community or is it actually 4? There isn't a super straightforward answer to this problem because we often don't know the underlying community structure for a given network. There are scenarios in which it may make sense to regard this as one community, and there are scenarios in which it would make sense to regard it as more. So one of the questions people have sought to ask in the past is, which algorithm is best for general network community detection? Now, that doesn't quite work for us because we're most interested in biological networks. So we sought to develop a benchmark and examine the relative performance of all of these algorithms, most of them available through the iGraph package for R, although MCL is its own thing, and evaluate their relative performance at problems specific to biology. So looking at those sequence similarity networks that I talked about before. Now, I want to emphasize this is different than past benchmarks. In the bottom left, I'm showing a sequence similarity network. And in the past, people have benchmarked the relative performance of community detection algorithms, but they focused more on graphs that look like this. These are graphs that have sort of uniformly distributed node degree and unweighted edges. This isn't a very realistic scenario for the problem we're trying to capture, so we developed a new benchmark that is closer to at least what we expect sequence similarity networks to look like. And the way that works is by refining this network in a number of ways. First, we switch from uniformly distributed node degree to power law distributed node degree. This is much more commonly seen in social media networks as well as sequence similarity networks and a lot of other real-world networks. Secondly, we added non-uniform weight distributions to all the edges. And most of this is taken from a very common graph benchmark called an LFR graph, if you're aware of that type of term. Lastly, the most new thing we added in our benchmark is collapsing weak edges to 0. And I want to emphasize what that means. In this graph structure, we have a lot of weak edges. You can see one here and one here and one here. And in biology, when we do these sequence similarity comparisons, oftentimes for very distantly related genes or genes that have very low similarity, rather than returning a match of, say, 20, 25%, they'll just return no match found. And what that means is that we get a lot of strong edges, but a lot of the weak edges are basically collapsed to 0. You won't find a lot of edges in the 15, 10% range. They'll just be zeros. And to get that sort of feel, we collapse any edges below a certain threshold that we change depending on the benchmark to 0, just essentially removing them entirely. So we ran a lot of benchmarks. I do have a time limit, so I'm not going to go super in depth on them. But in short, we varied the number of nodes, we varied the number of edges, we varied the distribution of weights among them, and we varied at what level we would collapse those lower weighted edges to 0. And what I'm showing here is the x-axis being the number of nodes, each plot being how aggressively we're masking. So the top left is removing no edges, the bottom right is removing the 30% weakest edges in the graph. And the y-axis being accuracy relative to the known ground truth on the synthetic benchmark using adjusted mutual information. It's a common way to measure community detection performance. Now, of these, a lot of the algorithms perform very well. The best performing algorithms tend to be label propagation and Louvain. I'm going to focus on them for the rest of the talk, as well as MCL, because it tends to be sort of a mainstay in the biological network algorithm community. So this is accuracy, but algorithms are more than just accuracy. Anyone that's written algorithms knows that accuracy is often a trade-off with runtime and other computational requirements. So as we kind of move into the modern age of big genomic data, we have to be aware of what problems we're looking at. Now, each organism has its own genome. Each genome has thousands of genes in it, and every gene we add to one of these sequence similarity networks adds an edge per existing genome in the set. So as we move into thousands or tens of thousands of genomes, our network size is going to grow quadratically with the number of genomes we have. And that wasn't really an issue back in the day, but nowadays we have thousands and thousands of genomes, and to be able to construct these gene families across thousands of organisms isn't really feasible, or is going to be extremely large networks. Any algorithm we have has to be able to process extremely large networks. So we wanted to look at what the runtime of these algorithms are. They're doing well, but how long do they take to do it? It turns out that as we scale up to around 50,000-ish genomes worth of data, and this is on synthetic networks that are representing sort of a very easy case, so a best case scenario, these algorithms are taking hours to years to finish. And just to put it in perspective for non-biological people, 50,000 genomes, these are networks with around 1 billion nodes in them, and extremely sparse edges, just to give it kind of a best case scenario. So you can see MCL at the top is taking around 4.5 years to finish. In the best case, we have set 8 days for label propagation. And there was actually a faster version of label propagation called Fast Label Propagation introduced very recently. It has the same performance, but it runs faster. And you can see it takes about 6 hours. So you might say, great, we're done, right? We have an algorithm that runs in 6 hours. It does the same as label propagation. That's one of the better algorithms. That's pretty good for 1 billion nodes. Unfortunately, it's not that simple. Again, everything is about trade-offs. We have high performance, we have good runtime. The place we pay for it is in RAM usage. And if we look at RAM usage on these graphs, you can see that fast label propagation is paying for that fast speed by using a projected 300 gigs of RAM. 300 gigs of RAM is a lot. And all of them are requiring a lot of RAM. And that RAM is scaling linearly, so as we go even larger, it's going to require more and more. The problem is that over the past decade, memory costs haven't really changed. We've sort of seen a plateauing in the cost of memory. And so if we have linearly scaling memory requirements, we're going to have linearly scaling costs as we go bigger and bigger. And since our graphs grow quadratically, we're going to have quadratically scaling costs. We could use high performance computers, but not everyone has access to them. And so it's not super suitable for people to just assume that everyone has access to a computer with hundreds of gigabytes of RAM. Now, it's not all bad news. There is sort of a workaround that we could do. And it starts by pointing out that disk space is orders of magnitude cheaper than RAM. And in addition, solid state drives are still plummeting in cost. At least for now, they have exponential decrease in their cost over time, at least in the past decade. So maybe there's a way to leverage sort of like an old school computer science algorithm to leverage disk space given limited RAM requirements. So we sought to develop an algorithm that has good runtime scaling, that has constant memory scaling, and that approximates the performance of other sort of best performing algorithms so that we can do community detection on big biological networks. This led to our introduction of an algorithm we're calling ExoLabel. It's named this because it builds off of fast label propagation with a number of refinements, And EXO, because as much as we can, we're storing data out of memory, so on disk. So what does that look like in practice? I don't have time to really get into all of the nitty-gritty on how it is implemented, but I'd love to talk about it more. Feel free to email me or reach out. But in short, just to show the statistics, again, back to our memory usage, we're looking at 150 to 300 gigs of projected space for up to 50,000 genomes or a billion nodes. And if I plot EXO-label's performance on here, you can see that it only takes around 100 megabytes of space, and that scaling is roughly constant past around 100 genomes, sorry. Now, of course, we're not getting that for free. I'm not just creating memory out of nowhere. We do pay for it in disk space, and you can see in purple that EXO-label does consume a projected 90 gigs of disk space, which is a lot. And that scaling is non-trivial. But at the same time, if you think about what you have access to or what the average person does, I mean, my phone has more than 90 gigabytes of disk space and more than 100 megs of RAM, whereas I don't think a lot of people have access to a computer that has 300 gigabytes of RAM alone, contiguously. So the scaling of that is constant in the space of RAM, and it's linear to space in the number of nodes and edges. And any people that are used to working on disk at this point are probably very ready for the next slide, which is the runtime, right? Disk space is notoriously slow. That's why a lot of algorithms move to RAM. It's much faster. But it turns out that, at least on sparse graphs in this synthetic case, EXO-label still tends to outscale larger algorithms. It's because it relies on disk space and it has that set up, it's not falling into swap space as these graphs get too large. And as a result, it can scale really well. So the runtime itself is log linear in the number of nodes and edges, and that ends up outscaling a lot of these more complex algorithms. So just a sanity check, we wanted to ensure that our algorithm is actually approximating the performance of the other more RAM-intensive algorithms, right? We wanted to have good runtime scaling and constant memory scaling. We've accomplished that. We also wanted to approximate the performance of other algorithms. So we took 50 prokaryotic genomes from RefSeq. This led to around 150,000 genes or nodes and around 850,000 edges. And again, these edges are non-zero similarities detected by our pairwise similarity search. If you're interested in the phyla represented, but shown here, it's a relatively diverse collection. So yeah. What we found is that our algorithm performs similarly to label propagation as we might expect. So what I'm showing here is a heat map of the similarity in communities identified on this network for all of the algorithms that we had in our test set. Where darker, like here, is more similar, and lighter, like here, is less similar. And you can see that EXO-label, which is shown here, is most similar to these other three algorithms. And just to kind of expand it out, those three algorithms happen to be label propagation and fast label propagation, as you can see here, which is very similar in this dendrogram. And then to a lesser extent, sort of MCL under certain parameters. So it does recapitulate the performance of comparable algorithms that use more RAM space, but are using mostly disk. So just to sum up, EXO-label enables scalable community detection on sequence similarity networks that get very big. It's also applicable to other networks. We just focused on the biology. It uses a max of 100 megs of RAM for arbitrarily sized networks, and the disk space scales linearly. The runtime is linear-rhythmic. It can outscale some in-memory algorithms at scale, especially under some hardware constraints. And the accuracy is comparable to other standard methods. I'll just note that EXO-label is distributed as part of the SynExtend package, which is available in Bioconnector. SynExtend builds upon Decipher. I'd love to use it, or if you find bugs, let me know. I will fix them. And just to acknowledge with my last few seconds, my lab, again, I'm from the Wright Lab at the University of Pittsburgh. My contact information is listed down here. Please check it out. Reach out to me if you have questions. find me at the conference if we'll be there in person. And thank you for listening.